Yeah, so hi guys, how you doing? So this is me learning multi-threading and concurrency. So I'm currently using a book I downloaded online, which is the Java concurrency. Yeah. So yeah, I'm just trying to understand the whole thing, and it's honestly sometimes tough to get like the whole concept of threading and concurrency. And yeah, I just like thought, let me just like be reading out stuff out, and then just like see how it goes step by step. So I've already done a couple of exercises for the first bit, where we're just like talking about the executor services, where you define a new fixed thread pool. And by the way, I'm using Java 25 to learn this. Executor service to define a fixed thread pool. Of course, you could have a cached thread pool, but for this case, I'm just like constraining myself to having 3 threads. And then yeah, I just like have methods. One, prepare a dish that just like prints out preparing a dish, and then it sleeps for 1,000 milliseconds. That's probably 1 second, I don't know. And then yeah, in case of an interrupted exception thrown, I just like do a thread.current_thread.interrupt, just like to show that the thread was interrupted. Yeah, so you could see a thread.interrupt. What it's ideally doing is let it like load the nodes and all. It should load all the nodes. Yeah, so dot interrupt. So what it's doing is interrupts the thread. So if this thread is blocked in an invocation of the wait long, wait whatever, you're passing in the time that it's supposed to wait for. So if the thread is blocked by an IO operation, an interruptible channel, then the channel will be closed, the thread's interrupt status will be set, and then the thread will receive closed interruption. So yeah, so that's just like looking at the whole concept. And as I'm learning, sort of like updating the notes. I keep on updating these notes and just like taking the notes etc while I learn the concept. So I've so far looked at the executor service. So what it's doing is providing an interface to manage thread pools, and then it has like a lot. The abstract interface defining the high level API for managing thread pools and executing tasks asynchronously. Focus on task management, so it encapsulates thread pool creation and management, providing methods for submitting tasks. That's interesting. Yeah. It also offers various implementations, so you could create a fixed thread pool for a fixed thread number of pools. I mean a fixed thread number. A cached thread pool for a pool that grows as needed. So yeah, if your whole like program requires like more threads, it would grow as needed. And then you have the single thread executor for sequential execution. So sorry again, I'm starting at the very middle or almost. Yeah. Yeah, but nonetheless, you just like have to keep on doing these things. Yeah. Okay. So next thing is what thread pool executor. So we just have to look at the thread pool executor, and what it's doing, it's a concrete implementation of executor service. It's the core providing fine-grained control over thread pool behavior. So thread pool executor. So let me just do this. What IntelliJ. So I've already talked about the flexibility. It offers all those things there. I'll just have to work with this. And then now we have this, what we call the thread pool executor. So thread executor. Yeah, and I guess what's doing is the core. It's the core implementation of that. So let me just read out. Let me just understand this theory, and then next possibly write down the notes. So core implementation of the executor service. What it's doing is it's the core. Provides fine-grained control over the thread pool behavior. So it's the one that is in charge of controlling the behavior of our pool. So granular control allows you to customize the thread pool parameters such as the following: core pool size, initial threads, okay, maximum pool size, keep alive time, idle thread timeout, queue capacity weightings. Okay, direct usage, so it involves instantiating it directly in your code, and then this approach gives you complete control over the thread pool's behavior, as you can specify parameters such as core pool size, maximum pool size, keep alive time, queue capacity. So ideally all these things that it's having like the granular control over. So it helps us control the pool size, the initial threads, the maximum pool size, so the maximum threads. Okay, keep alive time, so idle thread timeout, keep alive time, idle thread timeout. Oh, okay, that makes this, it makes a lot of sense. Then the queue capacity, so waiting tasks. So there's a queue, there's a core pool size, there's the maximum pool size, there's the keep alive, so checking like for the idle thread timeout, and then we have the queue capacity for that. So ideally that's what it's doing. So an example we have is I don't know if I should have it like this. So an example is this main method. We define the core pool size, the maximum pool size, the keep alive time, and then we're having a time unit, we're setting it to milliseconds. So yeah, so the task count is 15, so make this 4, 10, 12, 14, and finally 15, and observe the output. Okay, this is something you need to do. So array blocking queue, runnable, so creating array blocking queue, and then we have the executor. We pass in the fields, the pool size, the maximum pool size, keep alive time unit, and the working queue. So you remember those things that we talked about here. Queue capacity, so the waiting tasks. Work queue, what was defined as the work queue? So this is array blocking queue. Okay, and it has size 10. Okay, yeah. So let's do it. Let's get it. Yeah, so I guess you just have to do it. Yeah, so and then IntStream.range, so I just again I have to have it whole screen. We have the IntStream.range, we pass in the start, the task count, and then for each, what are we doing? Executor.execute, and then we're outputting something over here. Okay, let's try and understand what this code is doing. So in this example, the ThreadPoolExecutor is directly instantiated with specific parameters. It's creating a thread pool of a core pool size 2, and then it has a maximum pool of size 4, and then a keep alive time of 5,000 milliseconds. So and a work queue capacity of 10 tasks. So the number of tasks that are queued are 10. So the code uses IntStream.range, and for each to submit tasks to the thread pool. So I need to understand the IntStream, why we need it. Yeah, it uses that, and for each to submit tasks to the thread pool. So each task prints a formatted string containing the task number, current, pool size, and queue size. You need to select the right tool for your tasks based on the requirements. You may keep the following in mind. Okay, let's try and see that how that code would look like. So we have what we call the thread executor demo. Yeah, we have that, and then I'll just have to close all these other tabs. Thread executor demo, and then I don't know why it did this, so we possibly don't need this. Convert into a compact source, and then from there we look at what we had initially. So we define the core pool size, maximum pool size, and keep alive time. So let me just have it on my other screen so that I can just copy direct, and then I'll bring it back. So we say int core pool size. Our core pool size is 2, and then we say an int maximum pool size, which is a 4, okay, and then we have a long keep a lifetime 5000 like this, and then we declare a time unit unit equals to time. So I'll not fall for autocomplete, I just want to understand these concepts for milliseconds. And let's see what this time unit is doing. So time unit is an enum. Okay, so time unit represents the time durations at a given unit of granularity and provides utility methods to convert across units. So, and to perform timing and delay operations, it does not maintain the time information but helps organize and use representations that may be so it's mainly used to inform time-based methods, how long, how a given timing parameter should be interpreted. So the following code will time out in 50 milliseconds if the lock is not available. So we lock, and then we have the 50L, and then that means that the unit for that time would be milliseconds. So yeah, just like helping us do that. So we also have the int task count. So remember the task count. So yeah, and then after that we now use the array blocking queue, and then the array blocking queue we pass in runnable, and then we have working queue. We just like creating the work queue here, work equals to that, and then the task count, we just like have the queue have 10, the capacity, and then from there we create the thread ThreadPool executor, ThreadPool executor. Yeah, ideally that means I need to rename this thing so that it makes sense. ThreadPool, yeah, ThreadPool executor, and you can see, so we could call it executor and then equals to new ThreadPool, new ThreadPool executor, and then what we need to pass inside here is let's see, what we need to pass is the core pool size, maximum pool size, keep a lifetime, the unit, where is the unit coming from? Yeah, the time unit is there. Yeah, it means that it's converting this keep a lifetime, its unit would be milliseconds. Yeah, so whatever you provide as the keep a lifetime would be converted into milliseconds, and then we pass the unit, yeah, and then we pass the work queue. So let's see, so anything else I'm missing? No. So after that we create an IntStream. So first I need to look at the ThreadPool executor, we see how it looks like. Yeah, it's a lot to swallow, it's a lot, but I guess ThreadPool executor also maintains some basic statistics such as the number of completed tasks, an executor service that executes each submitted task using one of possibly several pooled threads, normally configured using executors, factory methods. ThreadPool address two different problems. They usually provide improved performance when executing large numbers of asynchronous tasks due to reduced per task invocation overhead. Okay. Alright, so they are trying to tell us that we need a try with resources, because yeah, okay, well, but we'll cross the bridge when we get there. Then possibly now the next thing is we create the IntStream. So again we have to go and look at IntStream, what it does and why we need it. We do an IntStream.range. So we have a range of ints, and then the range is from 0, so it's from 0 up to the task count, I presume. Yeah, up to the task count, and then after that we do a dot for each task. No, that means that for each task, what are we supposed to do? So we have I, so here we create a lambda expression, we do an executor dot execute, and yeah, execute, and then what are we executing? So we need that runnable instance, or yeah, so like that. So what we're supposed to do is we're supposed to output s out. what happened? S out, and then what we're supposed to S out is a string dot format. So ideally, just like formatting that string, we need the task %d like that, executed, and then we have the pool equals to %d again, queue size queue size equals to %d again. Honestly, I'll just copy that, the S out statement, man. It's becoming a nuisance, yeah. Okay, let's see. Pool size string dot format, remove it. Okay, cool. So we have that, and then once it's done, so we need I guess we need a brace here or something. Yeah, okay, cool. So we do Control Alt L. Is it Alt L? Okay, awesome. Now the final thing is, remember to shut down our executor, and then we close it. Executor dot close. Okay, yeah. So I guess we can run the thing and then see what we get. Task exception, blah blah blah. Okay, let's see. So task execution main, concurrent, task rejected, exception in thread main, java.util.concurrent rejected execution exception. So task thread pool that lambda rejected from java.util.that, pool size 4, active threads 10. Okay, receive it executed, pool size task 2, pool size 4, queue size 9. I honestly don't know what's happening here, so I'll just go to GPT and see what this means. So I'll bring it here and then say ChatGPT, ChatGPT, and then yeah. Hi, help me understand this output, and then from this code in Java 25. Let's see what we get. Let's see. So your code uses a ThreadPoolExecutor with a core pool size of 2, the maximum pool size of 4, and an array blocking queue of size 10. You're submitting 15 tasks. The output and exception come from the interaction between the pool size, queue capacity, and the rejection policy, so on. So you understand. So the executor always keeps 2 threads alive even if idle. So we will always have two threads alive even if you're idle. Maximum pool size, the executor can grow up to 4 threads if the queue is full. Okay, so the work queue equals to array blocking queue. So this means that the tasks that can't immediately be executed by a thread go here. Oh, okay, so this is storing our pending tasks, yeah, the array blocking queue, which is really interesting. So I need to understand how the array blocking queue works and how it looks like. It's really interesting. I'm knowing about it now. Author is Dog Lee. So a bounded blocking queue backed by an array. This queue orders elements in FIFO, first in, first out. Then the head of the queue is that element that has been on the queue for the longest time. Yeah, first in. Yeah. The tail of the queue is that element that has joined or has been there for the shortest time. And then yeah, new elements are inserted at the tail of the queue, and the queue retrieval, blah 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 blah. Okay, so this is classic bounded buffer in which the size is start. The class supports optional fairness policy, so attempts to put blah blah blah, and this is how it looks like, which is interesting. So it takes any type of elements with held inside here. It could take anything. Okay, then let's have it. Yep, so we go back to GPT and see. So it's saying the keep alive is 5000 ms. Remember, the time unit is the one that is responsible for converting it into milliseconds. So this means that extra threads above the core threads 3 and 4 are terminated if they are idle for 5 seconds. Okay, so remember we have the core pool size of 2, so no matter what happens, we'll always have 2 threads. We'll always have 2 threads there for us to use. And then yeah, so that means that when thread 3 and 4 are idle for 5 seconds, they are terminated. So the default retention policy is if the queue is full and the pool is at maximum size. So if the queue is full and the pool is at maximum size, new tasks are rejected with a rejected execution exception. So if the queue is full, our array blocking queue, we're currently at 10, so new tasks are rejected with that. So let's see step 2. What happens when you submit 15 tasks? So let's simulate the execution. So submit task 0 and 1, the core threads are 2, so both tasks are executed immediately, and then our queue size is 0. Okay, let's see. Okay. Our capacity is 10. Oops. Our let's see what they're saying. So submit task 0 and 1. So the core threads 2. So both tasks get executed immediately. Okay. So the queue size equals to 0. So we're currently at queue size. Yeah. Okay. We'll understand as we continue. Then next is so submit tasks 2 to 11. So how many tasks are we having? 15. So 10 tasks. So queue can hold 10 tasks, so they are added to the queue. Or when you're submitting tasks 1 and 2, our queue size is initially 0. And now we handle like 10 tasks. So this means that the queue can hold 10 tasks, which we've said the array blocking queue is holding the 10 tasks, and then they're added to the queue. Then the pool size stays at 2 because the queue is not full. So the pool size stays at 2 because the queue is not full. Okay, let's see. How many tasks are we submitting? 15. Where are we passing that task size, task count? Oh, this is where we're passing it. For each, we execute something. Okay. We continue and understand. So the pool size stays at 2 because the queue is not full. We are having let's see. So submit tasks 12 to 14. So the queue is full, 10 tasks. Okay. Crazy, you know. So the queue can hold 10 tasks. So they're added to the queue. 2 to 11. But these are 10 tasks, so it means it's full, yeah? So, okay, from 12 to 14, the task is full. So pool can expand to max 4. So threads 3 and 4 are created. So once our queue is that and our pool, so our queue is full, so it means that we need more threads. Is it really? So tasks 12 and 13 are executed by the new threads exactly. So task 14 has nowhere to go. So pool is at max threads and the queue is full. So we get a rejected execution is thrown. So let's see if we reduce the number. Yeah, let's see. task, we give it as 10 and run. Yeah, and everything happens as it should be. So task 0 executed, pool size 2, queue size it's 8, 7, 6, 5, 4, 3, 2, 1. So yeah, the first two tasks are executed with the core pools, the two core pools, and then yeah, is it really? Yeah, I guess so. Let's see. So that is that. So that is why we are getting that error. So the pool size was yeah, we just like had something extra in the queue which was had nowhere to go. Task 14, it had nowhere to go. So this means steps. So that's why we got that error. It was rejected from the ThreadPoolExecutor. Yeah. Key points from the output is 0 executed, pool size 2. Yeah. Key points from the output: 0 executed, pool size 2, blah blah blah. Task 2 executed, pool size 4. So notice that the pool size changes from 2 to 4 as extra threads are created. So let's see if we had any extra threads created. Pool size didn't change, so let's see. Let's have something like a 12 here. See if we need. Pool size is just like always at 2. It's crazy, 14. Yeah, so when you put 14 is when we get like more. We get like, it starts with a pool size of 2, and then we get pool size of 3, 4, and then from there it gets to 4. So yeah. So yeah, I'll just use AI again to explain that concept, but nonetheless. So notice how the pool thread changes from 2 to 4 as extra threads are created. So the queue size fluctuates because tasks are being dequeued as threads become free. So okay, so how to fix the exception? You have 15 tasks, but your pool and queue could only handle 14. So you have 4 threads and 10 queue slots. Task 15 will always fail, so you can fix it by increasing the queue. So the queue could hold 15. So let's see what our queue was holding initially. Our queue was holding 10. So let's see if we have our queue holding 15 and this one holding 15. I guess that was the task count, no? Was it 10 or 15? Let's see. Always 2. Always 2. Okay. Okay, so when we have 20 and all, we also like get the different things. Yeah, so I guess I now sort of like get the concept. So you have the task count being larger than what your queue could hold. That brings about the exception and all. Or you could also increase the maximum pool size to have more thread of pools that could support your thing. Or you could also use a different rejection policy. And then so executor.set rejected action handler, and then does this thing called new thread pool executor.call runners policy. So it makes the submitting thread execute the task instead of throwing an exception. That's nice. Okay, how to implement this? Honestly, I know little to nothing in these concepts. Yeah. Where do we call that runner? So before that, so executor.set rejected execution handler. So before the runner, so we say executor.set rejected, and then yeah, call the runner's policy like this. So we go again. Okay, we could try 20 and 15. So 20 as the task count, so the task that we have, and then what could be stored in our capacities, in our thing is, yeah, it works. So instead of throwing the error, what it's doing is set rejected execution handler, so to new thread pool, callers run policy. So let's see what it's doing. So what it's doing is rejection execution, so executes task R in the caller thread unless the executor has been shut down or blah blah blah. So executes rejected, a handler for rejected tasks that runs the rejected task directly in the calling thread. Yeah, I guess that's it. So instead of like rejecting it, we have a new policy to handle the rejected whatevers to, yeah. So when the queue is full, pool is also at maximum size. So instead of rejecting the task, the executor says, hey you, the calling thread, so run this task. So in your case, the main thread is, oh, the calling thread is main, so it's main is the one that would do the thing for us. So task 14, the one that was rejected before, will now be executed by the main thread, not like the threads that we have. Okay, so that makes sense. Okay, let's see how the output will change. So you'll see that you'll now see something like task 14 executed by main. Let's see the output. Where is task 14? Task 20, 19 or 19? Should be task 19, yeah. Okay, I need to know who executed what thread. So I'll just copy this whole code here. I guess it's because it's formatting of my whatever's here. Let's run it. Yeah, so we need to see what thread executed what. So task 14 was executed by main, because okay, now we are dealing with different numbers. So our task count is 15, our thread capacity is 10. So this means that thread that was it's task 14 because we are starting from 0. You have to remember that it's starting from task 0. So the last task, which was rejected, was executed by main. That's fantastic. It's good to know that. So we have the threads and all. That is fantastic. Yeah. Then possibly the last thing that I'll talk about here is I just want to understand the IntStream. I want to understand how the IntStream works and why and where we need it. Okay, let's see. So this is called Java thinking, not just syntax. Okay, let's go. Thank you for the compliment, GPT. So in simple terms, it's a stream of primitive ints. Okay, so a pipeline that generates numbers and lets you do something with each number. So instead of writing a for loop like this, instead of having the for loop, Java 8 lets you do this. So generating an int stream of 0 to 15. For each number, you're supposed to do something. So this is sort of like a lambda. So what exactly does this line do? Int stream, blah blah, that. So what it's doing is generating integers starting from 0, and then it stops before the task count. So if the task count is 15, it reaches up to 14. Okay. Range starts to end. It means that the end is exclusive, and then range closed starts to end. It means that the end is inclusive. So for each, do something. Think of it as a conveyor belt, 0 for each, 1 for each. Okay. So submit an independent task from here. You don't care about storing numbers, blah blah blah. I'll write your code without IntStream. I'd need a for loop, which is a lot of work. Okay. So never do this. Okay, thanks for that. So if you want, I could do this and this. So the key takeaway is a modern efficient replacement for counting loops, especially useful for task submission, etc. Okay, so let's see. So input stream range, say closed. I want to see those two extra tasks. What will help perform or perform the task? So task 14 and 15. Yeah. So it's weird. Task 15 got something to handle it, and task 14 was executed by that. So I need to understand that. So I'll just come back here again. When I have range closed like this from 0 to the task count, I get this. Okay, so y is task 15 executed by thread 3 and 14 by main. So nothing is wrong. Okay, the thread executor plus the range close plus the callers runner. Okay. So it's because we are having the caller runs policy. So we are having up to 15. The task count, so we are including range closed. We are including up to 15, and then the extra task of the root of your observation. So let's see, your executors had capacity, so let's compute this precisely. So the core threads 2, maximum threads 4, our queue would have 10 elements, so the total capacity before rejection is 14. Why is it 14? Or maximum threads. Okay, anything above 14. So how do we calculate the total capacity rejection? Calculate the total capacity rejection. Maximum pool size plus queue capacity. Okay, I definitely knew it was that, but I just wanted to be sure, Yeah, but nonetheless, at least we have our curiosity satisfied. So with range closed, so we are starting from 0 up to 15. So that means that we have 16 tasks. So overflow would have 2 tasks remaining. So why task 14 runs on main? When the executor is finally saturated, pool size 4 and then queue size 14, executor would execute task 14, so it's rejected. So after being rejected, the CallerRunsPolicy kicks in, calling thread to execute it. So the thread that is available is main, so task 14 is executed by main. This is intentional back pressure. So task 15, it goes to thread 3. This part is subtle and very important. Okay, so while main is busy executing task 14, worker threads are still running. They dequeue and complete tasks. Queue size drops, capacity becomes available. So when main finishes 14 and then submits task 15, a queue slot or worker is free. Executor accepts task 15. Okay, so we have some couple of seconds before they disappear. Okay, let's try adding some more numbers to the task count. So we have our pool as 10, so let's add it to 20. So that means that when we reach at 14, we'd be at capacity, so we have more like 6 more. So you see how. So that means that 14 would be executed by the main, and then the others would go to random threads. Let's see. So we have 14 executed by main, which is fantastic, and then let's look for 15. 15 is executed by pool that, 16 by thread that, 17 by thread that, 19 by thread that, and then 20 by that. So yeah, this is the output we get. So I guess that makes a lot of sense now. That makes a lot of sense. So this is our output that we get. This makes a lot of sense. This makes a lot of a lot of sense. Yeah. So how many tasks are we submitting? We're currently submitting 20 tasks. So that means that we are submitting, we're submitting 21 tasks because you're starting from 0. Yeah. So total is 21 tasks. Our thread pool maximum capacity is yeah. We'd have a total of 14 because 4 threads, 10 in the queue. So triggers the rejection handler. So when we get at task 14, so that means 15 to 20 would be executed by something different. So the CallerRunsPolicy does not mean only one task runs in main. It does not mean only one task runs in main. It means that every task submitted while the executor is saturated runs in the calling thread. So if saturation happens multiple lines, main runs multiple tasks. Okay, fantastic. So 18 goes to main. Yeah, so that means it could pick any as long as our thread, as long as every task submitted while the executor is saturated runs in the calling thread. Okay, so that makes a lot of sense. So that's why you're having 14 and 18, because 14 goes to main, 15, 16, 17. That's weird. That's so weird. So saturation happens again later. So this is subtle. So while main is busy executing 14, worker threads are running and then the queue is shrinking. Okay. So the main resumes submission, queue fills again, second saturation, task 18 hits it. So I guess that's when it meets that. So why pool size and queue printed look wrong, read during execution, etc, etc, etc. So yeah, I guess like now I have a clear picture of the thread pool and how it happens, how it works, and just like how it manages the task. So use ThreadPoolExecutor when you need precise control over thread pool configuration and behavior. I use executor service for most cases, benefiting from its simplicity and flexibility in choosing appropriate implementation. So when you want like precise control, just go for ThreadPoolExecutor. When you are you want to benefit from simplicity and flexibility, go for executor service. Yeah, I guess next we'll talk about synchronization and coordination. And yeah, that's it for up to this point. Thank you for joining in and see you next time. Remember to subscribe if this content made you smile. Adios.